All right, now we're going to talk about something that's one of the most important concepts of all of physics. It's conservation of linear momentum. Later on, we're going to have angular momentum, but now it's just linear momentum. Okay, so most of the semester, we've been really concerned with just one object, right? You know, like we draw, a force diagram, we got to figure out what's the object, and, stuff like that. I mean, when we talked about energy, we said we have to talk about a system, right? But, generally speaking, there was like a system of interest in an object that you were interested in. Okay, like let's say we collide two balls. So we have this ball colliding with this ball, So there's a collision, right? And, we say that this ball exerts an impulsive force on that one, this ball exerts an impulsive force on that one, and then, but I mean, let's say we knew the initial velocity of this guy, and we could calculate the impulse, then we can calculate the final velocity. But I mean, basically, we've always said just one item, right? One object, pretty much, Well, now we want to actually talk about both objects, okay? We want to consider both objects, not just one object, right? So let's say that these were on a table, these balls, okay? And let's say that the friction between each ball and the tabletop, that's pretty much small, so we can ignore it, all right? And so if I shot both balls, okay, after I let go, are there any horizontal forces on the balls, right? So again, I shoot the balls towards one another. We're ignoring the friction, because it's small, especially if it's like a solid steel ball and it's going really fast, Okay, so after I let go, what's true about the sum of the horizontal forces acting on the balls? It's zero, right? Zero, zero. Okay, so that, by the way, is called an isolated system. Now notice, though, got to be careful. It's only an isolated system along the horizontal plane, right? Because, gravity's pulling down, right? So it's not isolated that way. But we're just concerned right now with the horizontal. So it's isolated system along the horizontal plane. Okay. So you say, whoopee! Who cares? Well, you'll see. Okay, so let me show you something. And this is a proof, not a proof, derivation. And you see it a lot in physics. I mean, the method, I guess. So I just want to show you. Okay, so here's Newton's second law. I'm going to write it with all its, the sum sign and everything. The sum of the external forces, right? Sum of the external forces equals ma external, right? No kidding. I'll just say ma. Come on, right? You can't say external acceleration. Sorry, that was stupid. Anyway, sum of the external force equals ma, which equals dp dt. Yeah, right? Remember Newton like that? dp dt. Okay? And this is the total. I should have said total. Yeah, much better. Okay? Sum of the external force equals ma total, which equals dp total dt. Now, if the sum of the external forces equals 0, then this whole thing is 0, right? Then dp dt equals 0. Now, what did you learn in calculus? If the derivative of something is 0, the something is a constant. So if this is true, then that's true, which implies that P total equals constant. Now, that's just math, come on, but it's incredibly important because it means if you have an isolated system along some particular direction, that means that the momentum along that particular direction or plane or whatever never changes, no matter what, okay? So, all right, that's the important thing. No matter what, I don't care what kind of collision you have or whatever, if you don't have any external forces, that momentum before and after never change. And come on, how many things in nature never change? Not very many. So this is a big deal. And we'll do some examples. All right, we'll do some examples. Okay, let's say we have a collision in midair. So, so here's the floor or the ground, and I shoot a ball this way, and I shoot a ball that way. Oop, whatever. Okay? Again, are there any horizontal forces? We're ignoring air resistance. Are there any horizontal forces? No. So this is met along the horizontal plane, so the momentum is going to be constant. Okay? But it's not conserved in the y plane, right? Because gravity. So this is not true in the y plane. So that's why you got to be careful, Sometimes momentum is conserved along one plane, but not the other plane. It's got to be careful. Okay, all right. So this is a big deal. All right, big deal. Momentum is conserved. So for an isolated system, and that means sum of the forces is 0, momentum is conserved. That's the same thing as saying dp dt is 0, because p is constant, right? P is constant. So that means that P initial equals P final. P never changes. Incredibly important. Now, there are two types of collisions. Now look at, we're only talking about isolated systems. So that means momentum is conserved. Okay? But two different types of collisions. Okay, this one. So we're assuming that these are perfect, solid spheres. And when they collide, there's no deformation of the surface or anything like that. And so, okay, we know that momentum is conserved because it's an isolated system. But if these things are super hard and they don't they don't squish each other or they don't deform each other, kinetic energy is also conserved. Again, it's going to be like pool balls, That's a good example. It's not perfect, but it's close, right? So if you have both kinetic energy and momentum conserved, that's called elastic collision. Or you could say like two solid steel balls or something like that, right? So this is conserved because it's isolated, but if kinetic energy is also conserved, it's called elastic collision. Just the name, elastic collision. Now, let's say we have grapefruits, all right? So, these are just going to bounce off each other, right? No kidding. But if you have grapefruit, especially if they're like old, are they going to just bounce off each other? No, they're going to kind of deform each other, right? They're going to bounce a little bit, but they're going to deform, right? They're going to deform. So that's called an inelastic collision. Momentum is still conserved, no kidding. It's isolated, but the kinetic energy is not conserved, right? Because some of that energy is wasted when they kind of squish each other, Okay. So let's do an example. So this is a perfectly inelastic. What do you mean perfectly inelastic? So perfectly inelastic means that this one hits this one, and then they kind of become one. You can imagine, let's say we had like a car going this way and a car going that way, and they hit each other, and somehow they just stick together, right? And then they move off as a unit, So that's inelastic, correct? They don't just bounce off each other, right? They don't. Okay, so and it's called perfectly because they joined each other, right? Okay, so here's just an example. So this is sphere with mass m, v1, hits sphere, mass m, going at v2. So this is the before the collision. This is after the collision. And again, they're joined, so they have mass of 2m, and they have some velocity v, okay? And let's say, well, here's the question, all right? Okay, so what is p before? Now, when you write it like that, that means you want the total momentum before, okay? The total momentum before the collision. Well, that's easy because, momentum is just mv. So the total momentum before is just the momentum of this guy plus the momentum of that guy. Momentum of this guy is just mv1. This one is just mv2. Okay? So the total momentum before is just mv1 plus mv2. Okay. What's the momentum after? Well, we just have this one object now because they joined, right? And momentum is just 2m times v. So the momentum after is just 2mv. Now, we're assuming that this is, I don't know, let's say it's in the air along the horizontal plane. So we have an isolated system along the horizontal plane. So that means the momentum along the horizontal plane is conserved. So that means that this has to equal that. Okay? So you just say, so mv1 plus mv2 equals 2mv, right? Momentum initial equals momentum final. So to calculate v, just divide by the 2m. All right, that's true, but you can get rid of all the m's. Might as well. And there you go. So that's always going to be true in a situation like that. Always. I don't care, what these velocities are. It doesn't matter. This is always going to be true. Let's make it look nice. Okay? It's always going to be true. And come on, that was simple, And it's just because momentum is conserved. That's all it is. All right. So let's see. Always, right? Always. Okay. Okay. Now. Okay. So here's what's called an elastic head-on. So this one is stationary, right? And this one is moving. And we're going to say it's an elastic collision. So they're like hard spheres, okay? They're not rotten grapefruits. And so what's conserved? Well, it's an isolated system. We're assuming that. So momentum is conserved. Okay, we're told it's elastic, so kinetic energy is also conserved. All right? So, and what we want to do is, like it says, we want to find the final velocities. Okay, the final velocities. Okay, so let's do it. So we have m1v1 initial plus m2v2 initial equals m1v1 final plus m2v2 final. So that's momentum conservation. Now let's do kinetic energy conservation. So kinetic energy conservation is 1/2 m1v1 initial squared plus 1/2 m2v2 initial squared equals 1/2 m1v1 final squared plus 1/2 m2v2 final squared. All right, now what do we want? Again, what we want the final velocities, right? We want V1 final and V2 final, right? So that. Okay, so two equations, two unknowns, right? Well, it's actually going to be a lot of work, and we're not going to do it. Lazy, right? We're not going to do it. So I'm sure it's done in the book, but it's just a lot of algebra. But, you have to admit, we could do it, right? We could do it. Of course, V2 initial is 0, so we'd get rid of that. But still, it's going to be a lot of algebra. So the book shows you the steps. I'm just going to give you the answers. So these are the answers. So V1 final is that. You can see it depends on the masses, and it depends on the V1 initial. Okay. V2 final depends on the masses, and it also depends on V1 initial. So they all depend on V1 initial, and they all depend on the masses, but in a different way, right? This here is different than that. Okay. Now, should you memorize those? Certainly not. I mean, you get better things to do. But you should, put a marker on that page where those formulas are found, because you're going to use them for some of the homework questions. And if you need it on a test, just like anything else, I'll give them to you. But yeah, you should know where these equations are, because they're important. Now, I want to just show you some things with these equations, and you'll use this in your lab. So you'll have a lab on momentum, and what I'm going to show you, you're going to use. So let's just look at some cases, some different situations using these equations. Let's see. Let's say that M1 is less than M2. Okay? So let's say that, I don't know, let's say this is a steel ball, and this is maybe a golf ball. All right? Okay, so what happens? You know, have you ever done this? So this is this kind of massive steel ball. You have this, you know, not so, hey, let's do this. Let's say this is a steel ball and a ping pong ball. All right? So you're shooting a ping pong ball at this steel ball. So what happens to this thing? It hits this big, massive steel ball. Does it keep going this way or does it go that way? Well, let's figure it out. Okay, let's figure it out. So let's use the equation for V. Let's just do this one. Okay, let's do that one. So V1 final. Now notice it says M1 minus M2. Okay. Now, okay, and I said that this one is less than that one. So this is 1 kilogram, this is 2 kilograms. This is going to be negative, right? This is going to be negative. This is going to be positive. So that means that V1 final is going to be some negative number times V1 initial, right? So V1 final is going to be less than 0. That's all I wanted to point out, okay? Because this is less than that, so this is going to be negative, okay? So that agrees with our experience, right? If this is more massive than this is just going to hit it and bounce back. All right, so it's going to bounce back, right? So it bounces back. Okay, that's all I wanted to say about that. Let's do the case where M1 equals M2. Well, and all I'm looking at is this guy. I don't care about that guy right now. Okay, so if M1 equals M2, what's the denominator? What's the numerator? 0. Agree? 0. So if this has the same mass as this one is going to hit this one. This one's going to go flying, but this one's just going to stay put, right? V1 final is going to equal 0. V1 final equals 0. And you see that when you play pool, right? If you hit it head on, you know, one ball hits the other ball goes flying, the first ball just sits there. All right, let's do, okay, what's next, right? M1 is greater than M2. If M1 is greater than M2, that means this is bigger than that. So this will be positive. That will be positive. So that means this is going to be positive. So if this is more massive than this one just keeps on going to the right. Keeps going. So V1 final is positive. So it goes that way. Okay, so those are kind of boring. But now let me show you the real interesting ones. And this is what you're going to use on your lab. Okay. Let's say that M1 is tons less than M2. Okay. All right. So this is a ping pong ball, and this is like a tungsten or something. All right. You know, really dense. Okay. All right. So M1 is much, much less than M2. So this is a math trick. Okay, and you need to know it. So let's write the equation for V1 final. V1 final equals M1 minus M2, leave some space, over M1 plus M2 times V1 initial. Okay. M2 is tons bigger than M1, so divide by the big guy, the massive guy, M2, 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 okay? So we didn't cheat. We just saw which one is the more massive, and we divided top and bottom by that more massive one, okay? Now, what is M1? So what's this? What's M1 divided by M2 if M1 is tons less than M2? Well, it's basically 0. All right, let's put a 0 here. Okay. What's m2 over m2? 1. What's 0 minus 1? Minus 1. Okay. What's m1 over m2? 0. What's m2 over m2? 1. What's 1 plus 0? 1. Okay. What's negative 1 over 1? Negative 1. So therefore, V1 final equals minus V1 initial. Okay? That's what it is. Okay? So again, if this is ping pong, this is tungsten. This, let's say it's coming in at 5 meters per second. It hits it, goes back at 5 meters per second. So that's, okay? Let's do M2 final. M2 final, sorry, V2 final. V2 final equals 2M1 over M1 plus M2. V1 initial. Again, you divide by the larger of the two. Divide by M2. Let's do the denominator first, because we're silly. M2 over M2 is 1. M1 over M2 is 0. 0 plus 1 is 1. So we have a 1 on the bottom. But what do we have in the numerator? What's M1 over M2? It's 0. So the numerator is just 0. So that means it's 0, right? So therefore, V2 final is 0. Okay? So ping pong ball hitting tungsten. Ping pong ball, 5 meters per second. 5 meters per second. What does this do? It just sits there, right? It just sits there. And again, try it. All right. So you'll have to do some calculations just like this for your lab. Let's do the other way. Let's do M1 is much, much larger than M2. So V1 final, M1 minus M2, M1 plus M2, V1 initial. Divide by the larger one, which is M1 this time. Okay. M1 over M1 is 1. M2, the small one over M1, which is a large one, is 0, right? This is tons bigger than that, so that's 0. So the top is just a 1. Okay, M1 over M1 is 1. Wait a second. What did I do? Wait. Sorry. M1 plus M2 divided by M1. Yeah, okay. All right, so M1 over M1 is 1. M2 over M1 is 0. So we just get that. Okay, so does that make sense or what? If this is a big, solid, massive tungsten, this is a ping pong ball, this guy's going at 5 meters per second, what's it going to do? It's just going to keep going at 5 meters per second, right? What's a ping pong ball going to do to a tungsten, super dense tungsten ball, you know? Okay, so what do we see? We see V1 final equals V1 initial. So the speed of this guy doesn't change at all for this approximation. All right, let's do the other one. V2 final equals 2M1 over M1 plus M2 V1 initial. Again, you divide by the larger mass, which is M1. Okay, M2 over M1 is 0. M1 over M1 is 1. M1 over M1 is 1. So you get 2, right? So V2 final equals 2 V1 initial. Okay? So, all right. Okay, there you go. All right. So be sure you can do that little ratio trick there. Now, this is only good, you know, if this thing is at rest, right? Well, what if they're both moving? You know, what if they're both moving? So what we want to say, what we want to consider is V2 is not equal to 0. That's what we want to talk about now, right? So this is moving, and this is also moving. Okay? Okay. So here's a concrete example. So let's say we have this guy moving at 4 meters per second, and this one moving at 2 meters per second. But I don't want to, use momentum conservation and kinetic energy conservation to get new formulas. I don't want to do that. It's too much work. I want to use these formulas. In other words, because they're nice, right? I want to use these formulas. But again, these require this to be at rest. But I want to use those formulas for that. Well, how can I do that? Well, pause your video and think about it. Okay, I hope you've figured it out. Let me give you a hint. Let's say I can walk at 2 meters per second. What's that problem going to look like? What is this situation going to look like, according to me, if I can move this way at 2 meters per second? Well, if I'm moving at 2 meters per second relative to the ground, and this is moving at 2 meters per second relative to the ground, what's the speed of this relative to me? It's 0. What's the speed of this relative to me? It's 2. So guess what? If this one is at rest, I can use those formulas. Isn't that nice? So all you have to do in order to use these formulas is just switch your reference frame. Just basically do what you have to do to make this guy be at rest. Okay? So for this one, just assume that you're going in this way 2 meters per second. Then use these formulas, and then add the 2 meters per second later on. That's all you have to do. Nice, right? Okay, so there you go. Okay? So let's just do it. All right, let's just do it. Okay, so I should have left that on. All right, so now V1 final is going to be M1 minus M2, so 2 minus 1, so it's going to be 1 kilogram. And the sum is 3 kilograms. And then V1 initial, which is 2. So we get 2/3, right? 2/3 meters per second. Okay, and V2 final is going to be 2m1, which is 4 kilograms, over the sum, which is 3 kilograms, times V1 initial, which is 2 meters per second. 2 meters per second, which is 8/3. 8/3 meters per second. Okay? All right. So that's in this reference frame. But then we want to go back to this one. So what do? We just have to add, just add the 2 meters per second. Right? So I guess all I'm saying is that these formulas are really awesome. You can use them when this is at rest, or by switching the reference frames, you can also use them when this is not at rest. So these are really awesome equations. Okay. Here is a question for you. Suppose the entire population of the world gathers in one spot, and at the sounding of a prearranged signal, everybody jumps. So everybody comes to Hawaii. Bad idea. Coronavirus, all right? Okay, everybody comes to Hawaii, and they make a sound, and everybody jumps. While all the people are in the air, does Earth gain momentum in the opposite direction? So please pause your video and figure it out. Okay, well, when everybody is standing in Hawaii, what's the total momentum? 0. Okay, so are there any external forces? We're going to say no. So that means momentum is conserved. So that means if the initial momentum is 0, the final momentum has to be 0. Well, so here's the Earth. Here's everybody in Hawaii, right? If they jump this way, they have momentum m, that's the mass of all the people, v, which is that way. Now remember, we said that the final momentum has to be 0. So therefore, what has to be true? What does the Earth have to do? The Earth has to move that way in order to conserve momentum. So the answer is yes. Earth recoils like a rifle firing a bullet with a change in momentum equal and opposite to that of the people. Have you ever seen like a TV show if somebody has a pistol? You know, so they shoot the pistol and the bullet goes this way, but what happens to the person who holds the gun? They go that way, right? Because conservation of momentum. The initial momentum is 0, so the final momentum has to be 0. So that means that that momentum has to cancel out this momentum. Okay, nice. All right, now, so far we've talked about momentum in one dimension only, right? One dimension only. Well, what if there are 2 dimensions? There's nothing new, all right? There's nothing new. Momentum's a vector, so let's say we have a collision in a horizontal plane. Well, you can say that that's the x direction, that's the y direction, right? So momentum is conserved along the x and along the y, because it's all horizontal. So you just have 2 equations, right? You have conservation of momentum in the x, conservation of momentum in the y. And you'll do that in lab, okay? And for kinetic energy, it's a scalar, so it doesn't matter. All right, so we're going to do a problem in the next video. So let's quit. Okay.